Bismillahirrahmanirrahim. Good evening, everyone. Today, our lecture will talking about the built-in potential barrier, but at first, we will do simple review to the depletion region. Here, like we're seeing here to this diagram, explain the Hall diffusion, moving, and electron diffusion, when here at the middle x equals 0 to donor concentration and acceptor concentration at the p-type. Now, like we said before, at first, when the depletion region start to create, the holes start to diffusion, try to diffuse to another side, to the n-type N region, and the electrons will try to diffuse to the p-type. And when when the space charge region is created, after that, this space will try to prevent the other electrons and holes from diffusing to the both sides. And here, diffusion force on electrons, like we know, the diffusion force on holes, but the electric field will be from N-type to P-type, and we say why and explain all the reasons, because this thing has relation with the majority carriers and prevent the majority carriers from moving from the both sides. Here, we will examine the properties. We will focus on the properties of the step junction, but in thermal equilibrium. All our lecture will talking about thermal equilibrium. Here, we must know two important things. Number one, no current exists, like we said at the last lecture, and no external excitation is applied. And we will try to determine three things: the space charge region with it. This will maybe at the next lecture. Electric field and the potential through the depletion region. The analysis in this chapter will focus on two things. Number one, the Boltzmann approximation, and we know what that means, which means that each semiconductor region is non-degenerately non-degenerately depth. The second thing is that the complete ionization exists, which means that the temperature here in PN junction is not too low. Now, let's focus and explain our topic today. This topic is the built-in potential barrier. If we apply potential between P region and N region, what will happen? We will not be under equilibrium condition. That's important. We will not at the equilibrium condition at more. The energy Fermi level will not be constant through the system. Like we remember at the last lecture, we proved the Fermi energy level derivation of Fermi energy level equals 0. That means EF at the last lecture was constant. But here, when we put potential between P and N regions, that means we will not add the equilibrium condition at more anymore, and the energy Fermi level will not be constant at this system. Here, figure 7.3, like we see the conduction band at the P, after that start to bonding to reach the N-type, and here will be constant and keep going in N-type. And this difference equal the built barrier potential from conduction energy band at the P region from conduction energy band at N region. And here, thermal equilibrium, like I said before, here the condition energy band and valence energy band must bend as we go through the space charge region. Like we're seeing here, all the curves bend to reach another point, different point from its start point, except one, the Fermi energy level will be constant at the middle of this diagram. Here, like we said before, VBI, built barrier potential, it's difference between conduction band of holes and conduction band from conduction band and N side. Conduction band of P side, yes, from N side. And the same thing with difference between valence energy band at P side from N side, and the same thing with the intrinsic Fermi level and P side to N side. Here, EVBI, it is the built-in electric potential energy, and the important element here, QFP, it is the Fermi potential for holes in the P-type semiconductor. And here QFN, it is the Fermi potential for electrons in the N-type semiconductor. Let's take a look to this diagram again. Here, like I said before, energy band diagram of a p-n junction in thermal equilibrium, and we all our works today in this lecture will be at the same condition at the thermal equilibrium. Both barrier potential mentions to us equilibrium between something, between, this will be important, we must note it, between majority carrier electron in N-type and minority carrier electron in P-type. That's mean in type number one, region, sorry, number one, and P number two. At like we said before, at this diagram, P was from this side and N region from this side, and this mentioned to us equilibrium between relation between the majority carrier electron in N type in N region and the minority carrier electron in P region. And at the same thing between majority carrier, but majority carrier holes in the P region and minority carrier holes in N region. We must know that at the same situation, holes and here electrons from N to P. It's important. It's going to another slide here. Let's solve this important question. Why built barrier potential difference across the junction? That means it has the same equation, but except when it be near from the junction and can't be measured with a voltmeter, because a new potential barrier will be formed between the probes and the semiconductor will cancel the built barrier potential. The built barrier potential mentions equilibrium. So that's mean no current is produced by this voltage. And like we know, the built barrier potential can be determined as the difference between the intrinsic Fermi level in P region from difference from N regions. Now, to prove the equation of built barrier potential existing between two extrinsic semiconductors at the same condition, but between two extrinsic semiconductors. Let's go to my notes. Let's share. Let's new share again. Yes. To find the built barrier potential existing between two extrinsic semiconductors, we will start from equation 7.1 at the source, and the most important equation will be something like start point to us to can approve and calculate this result, this goal. We will start from this equation, EVBI, electron bulk barrier potential, equal the whole conduction band minus electrons conduction band, energy band. Here, that's mean we must calculate at first one of them. We will start to calculate the electrons conduction band. We can calculate this result, determine this result by using the concentration electrons from this equation, equal the effective density to the conduction band at the conduction energy level, exponential between two brackets, Fermi level minus electron conduction band divided on Boltzmann constant temperature, 7.2. And at the same time, like we know, we have two equations. We can determine concentration of electrons by using one of them. Here, we will depend on equation 7.2 by divided this equation on effective density of electrons to be like here, and after that take length to all the equation to take this bracket alone equal Boltzmann constant temperature, then donor concentration divided on effective density of conduction band. Now let's take this, let's calculate just this result to electron conduction energy band, equal Fermi level minus Boltzmann constant temperature dot length donor concentration divided on effective density of conduction band. This will be important because this important element here to can calculate the electron belt barrier potential barrier. Okay. Now we will start to determine the hole's conduction energy band. We will start from these equations, hole concentration equal effective density of valence band exponential holes valence energy band minus Fermi level divided on Boltzmann constant temperature. Like we know when we say P-type, that's mean P naught equal the concentration of holes equal concentration of acceptors at the, yes, here we will instead displace by using NA result, and after that divided on this equation on effective density of valence band, take length like before to calculate this result about this bracket equal Boltzmann constant temperature length concentration of acceptors divided on effective density of valence band. And after that, dot all this equation with -1 to make this bracket be like Fermi energy level minus whole valence band and valence energy band equal minus Boltzmann constant temperature length NA divided on NV. To make to do something like simplify to this equation, we can do another math trick. Just we will put NV up and NV up, and NA will be at the bottom level here, bottom place. Here we will do another math trick to make this equation be easier or more simple. Just we will put whole of conduction energy band minus whole conduction energy band. Like we know, this bracket, the last result to this bracket equals 0. That's mean after that, just I will replace this element again, okay? Just I will put the Fermi energy level minus whole conduction band together plus whole conduction band minus whole Fermi whole valence energy band. Like we said before at the last lecture when was talking about energy band gap, we say the energy band gap equation equal whole conduction energy band minus whole conduction valence band. That's mean we can simplify this equation more by put here energy band gap, because that will be Fermi energy level minus whole conduction band plus energy band gap equal Boltzmann constant, temperature, length, effective valence, NV divided on concentration of acceptors. Effective density of valence band, of valence energy band, yes, divided on concentration of acceptors, that's right. To find here our result, what was our result? Our result was talking about try to determine the holes of conduction band, okay? Here, that's mean we can easily determine the last result of whole conduction energy band equal Fermi level plus energy band gap plus Boltzmann constant, temperature, length, effective density to valence band divided on concentration of acceptors. Now we have the two important elements. Like we say before, I don't know how I can write some notes here. Okay, now I have the twice results, the whole conduction energy band and electron conduction band, and we can calculate easily the electron bolt barrier potential. After we putting all this equation together to calculate EVBI, here EVBI will equal energy band gap plus Boltzmann constant T ln NA ND divided on NB NC. Okay, but we can make another math trick to calculate, to make this result, this equation be more easy. For example, we can calculate one of them to simplify this equation, and after that put this result inside this equation and determine it, calculate it again. We prefer starting from here. We know equation has this element inside it. By this trick, we can calculate the energy band gap, and after that put this result inside this equation and determine all of that again. Okay, let's start from square intrinsic carrier concentration equal effective density of electrons dot effective density of holes at the valence band exponential minus energy band gap divided on Boltzmann constant temperature. We will find the energy band gap from this equation, let's divided on NC NV here, and after that take length to all of that and dot -1. That's mean here energy band gap equal minus KT ln intrinsic carrier concentration square divided on effective density to electrons dot effective density of holes. To cancel this minus, just we will NC and we will put it up, and an intrinsic carrier concentration square will be at the bottom. Okay. Now we will put this result. If we want to cancel this minus, we can do this math trick and we can put it like it, okay? We will put this equation, we will put this result, this equation to energy band gap here and determine all this equation again to calculate the result of electron belt barrier potential. After that, the last result will be to VBI, that's mean belt barrier potential equal Boltzmann constant, temperature divided on electron charge between two brackets, effective density of concentration of acceptor dot concentration of donor divided on intrinsic carrier concentration square. And to simplify, to make this equation easy, more easy, just we can put VT. VT, that's mean the thermal potential, or we can say thermal voltage here to be belt barrier potential equal thermal potential or thermal voltage dot concentration of acceptors dot concentration of donors divided on intrinsic carrier concentration square. Here we have note, important note, from this point on in the text, here donor concentration and acceptor concentration will denote the net donor and acceptor concentration in the individual N and P region. Individual, okay, will be individual N and P regions. Now let's come back to our notes. Let's do that, new share again. Yes. Like we see here at figure 7.7 shows the energy band diagram of the PN junction for the case when positively voltage is applied to the N region with respect to the P region. Here, the potential hole from intrinsic Fermi level to whole energy valence to the whole Fermi energy level. And here EV total equal, like we're seeing here, the difference between the conduction band at the P type and the conduction band at the N type. And here, like we see the intrinsic Fermi level bound like the conduction band and valence band. Sorry. Here, the electron potential equal the difference between the energy valence band from electron Fermi energy level from the intrinsic Fermi energy level. This 7.7 figure, like I said before, energy band diagram of a PN junction under reverse bias. That means some different. And we will explain all the important details at the next lectures about the reverse bias, because it's an important topic. The conductive course and solar cell course shared the same topics, and the reverse bias, it's one of them. Here, as the positively potential is downward, the Fermi energy level on the N side is below the energy Fermi level on the P side, like we said before. And here, the whole Fermi energy level minus electron Fermi energy level equal the applied voltage and units of the energy. The total potential barrier indicated by V total has increased. Okay, the applied potential in the reverse bias conditions. We will talk about this at the near future. Like we said before, VR is the magnitude. This element is important. What is the VR? The VR is the magnitude of the applied reverse bias voltage We'll explain all of that the next lectures. Like I said before, I depended totally on the chapter 7 to this book, and this the name's book, the author. Thank you about your listening, your patience. I will see you at the next lecture. Let me stop recording.